Welcome everyone back to 264A, Automated Reasoning. We'll continue our discussion on tractable circuits today. We did a review of NNF circuits and the knowledge compilation map last time. So what we'll do today is we'll be zooming in on one of the circuit types, which is decomposable negation normal form, which is characterized by the property of decomposability. And what we'll do over the next few lectures is basically zoom into a few more circuit types that have been influential. So what we'll do is see why decomposability gives you tractability and what kind of operations become tractable once you have decomposability. And we'll look at these in some detail so you become quite familiar with them. I have asked the TA to post a paper for your reading. This paper is actually quite detailed and has more material than what we're covering, but you should be using this, the lectures and the corresponding slides as your guide of what we're really covering, and basically look up the material that's relevant to that from that paper. Of course, you can read more, and we will be posting the slides later from the last couple of lectures. We're just organizing them based on what we're covering. All right, I will head back now to the whiteboard so that we can start our discussion. All right, so as mentioned, we will be focusing on the property of decomposability today. And this property gives us a type of circuits known as decomposable negation normal form, or d-DNNF. And remember what the big picture here is. We do have this notion of a tractable circuit. As discussed last time, the ones we'll be discussing will all be based on the notion of negation normal form circuits and subsets of them. And the idea is if we have one of these tractable circuits, then certain queries become tractable in the sense that we can answer them in polytime on these circuits. These are queries that are generally hard, for example, when applied to CNF and so on. And as part of our discussion later, we'll talk about compilation. How do you compile a Boolean formula, typically in CNF, into one of these circuit types? But let's keep going here. And as you remember from last time, we're interested in a number of questions and transformations that we can do on these circuits. This is the list of queries or questions that we can ask about these questions. Of course, there is more, but this is the focus here. And as you recall, a number of these are quite familiar. Consistency, there is satisfiability, there is validity. We had three types of entailment, whether one circuit type implies another, and whether a circuit implies a clause, and whether a term implies a circuit. And these distinctions are meant because the first type, which includes the other two in a sense, can be more difficult, and the other two types can be easier. They still have applications, and sometimes we can do this, for example, but we cannot do that, and it's useful to know that. And then there is equivalence testing, testing whether two circuits are equivalent, model counting, and model enumeration. We also talked about transformations, and this is when we take circuits and transform them. So I can take one circuit and existentially quantify, let's say, variables X and Y from it. I can take a circuit and condition it on some literal or more than one literal, and so on. I can take two circuits and conjoin them. I can disjoin them, or negate a circuit. And the idea here was I want the result to be of the same circuit type. So if I'm taking two decomposable negation normal form circuits, and I conjoin them, I want the result also to be a decomposable negation normal form circuit. And that's why this may not be easy to do. All right, so here's the property of decomposability. This is something that you really need to know, this property. And the review here is that it's a property that applies to AND gates in our NNF circuit. And here's one of the AND gates that are being highlighted here. And if you recall what this property says, if you look at the subcircuits that are feeding into the AND, they should be over disjoint variables. And in this case, it's pretty simple because we have only two subcircuits feeding, and you can see that one of them is over the variable CD and the other over the variables AB, and those do not overlap. So we will say that this AND is decomposable, and this has to apply to every AND in the circuit. And when that's the case, we will say the circuit is decomposable, and the circuit type is known as DNNF circuit, right? So it's a pretty simple definition. And let's take a look at a concrete example. In this case, I have a little Boolean circuit. I have two inverters that are cascaded. The input is A, and this gate is called X, this gate is called Y, and the output is C, and this is a knowledge base that basically describe that circuit behavior. And you can see what's going on here is, the idea is I want to talk about the behavior of the gates, but these gates may not be okay, may not be functioning correctly. But assuming it's functioning correctly, then if I have A, then the output would be not B. This is an inverter, right? It inverts its input. And if the input to this X inverter is false, then the output is true. Okay, so I'm conditioning that on the gate working. We'll see that later when we get to one of the applications on diagnosis. You'll see similar things, because in those applications, we want to reason about the behavior of systems. And when they're not functioning properly, I want to know what happened, what may have went wrong. It's a problem that has, or the formulation of that diagnosis problem has applications even beyond diagnosis. Anyways, here's also the behavior of the second gate. And similarly, I'm saying that this gate inverts its input when it's behaving normally. Now, what I'll show you next is how this would look like if we compile this into a DNNF circuit, something that you may want to do if you're doing, for example, diagnosis applications. And here's how it looks. So this is now the circuit type, DNNF, that is equivalent to the knowledge base that I showed you earlier. And you can see here our literals sitting at the bottom. And there's only two AND gates in this case. There is this AND and there is that. So if I want to verify whether this is decomposable, I need to check those two guys. So if you look at this first guy here, you will see that there are three subcircuits that are feeding into it that are color-coded, this, and that. And if you look at the variables in the first subcircuit, that would be B, in the second one, A and OK X, and the third one, C and OK Y. And you can see these guys do not overlap. So this is indeed decomposable. And similarly for the other AND gate, you will find that it's also decomposable. So this is indeed a decomposable negation normal form. Very good. So this is the property, this is the circuit type. And most of what we'll do today is look at operations on these circuits that are generally hard, but they become easy if the circuit is decomposable. And you'll see that most of these operations, when applied to these circuit types, they end up obtaining their answer by simply traversing the circuit and doing simple things at every gate. So there will be linear time operations. And we'll try to discover some of these things together. And we're going to start first by satisfiability. So we know satisfiability is NP complete. And on CNFs, it's hard. We spent a lot of time actually looking at algorithms for testing the satisfiability of CNF formula. And now let's see what happens when my knowledge is in the form of a d-DNNF circuit. And for this particular guy, well, we'll probably help you with this one first, but then when we go to the other operations, you'll see the style of how we do satisfiability here, and then you'll probably derive some of the other operations we will do. So, well, before I do this, here's the style of the algorithms we're going to be looking at. Look, when you see a circuit like this, we'll end up having to handle a certain number of cases. There's the base cases, which are the leaves, and those are literals. Now, in general, we didn't mention this, but you could also have constants, true and false, at the leaves. So the base cases that these algorithms will have to consider are either constants, true, false, or literals, positive one like this, or negative one like that. Now, aside from these base cases, and given the definition of NNF circuits, we will only have to consider two recursive or non-base cases. And those would be ORs and ANDs, right? So basically, everything we're going to be doing here is going to be saying, okay, what are you going to do if the node of the circuit is true? What are you going to do if it's false? What are you going to do if it's a positive literal X or a negative literal X? And then what do you do at a node alpha or, alpha 2, alpha n? And finally, what are you going to do when you have a node alpha 1 and alpha n? That's it. If you manage to figure these cases, you've got yourself an algorithm. And let's see it for satisfiability, right? So what I'm going to show you next is equations that handle satisfiability for these guys. And here they are. Now, these equations, when we apply them to the circuit, you will see that they will lead to a linear time procedure. And I will illustrate it next. But before I illustrate this, there are 6 equations here, and let's number them 1, 2, 3, 4, 5, and 6. And the claim is, out of these 6, there are 5 that always hold, but there's only one of these guys that will only hold because of the property of decomposability. So, and then I want you to identify that. So let's look at these starting from the bottom. So if I give you false, is false satisfiable? Obviously not, right? So that's easy. What about true? Is that satisfiable? Yes, that's also easy. What if I give you the literal not X? Is that satisfiable? Yes, because you can simply assign X the value false. So whenever we're looking at the what's inside the parentheses, we'll view that as our only knowledge base, right? And similarly, what about the positive literal X? And this literal is satisfiable because I can always say X is true and then I can satisfy that formula. So now what it gets interesting is these 2 recursive cases here. What about an OR? What about an AND? And someone already asked, are these in general true, 1 and 2? So the claim is one of them is always true, but one of them and the other is not necessarily always true. Can you identify the one that is always true based on your intuition? So remember, what is satisfiability? I'm trying to find a variable assignment. So in this case, A or B will be arbitrary formulas. That's probably not a great notation because we're using X and not X to talk about variables here, but think of A and B as arbitrary formulas. So typically we've used alpha and beta for these guys. Okay. So someone is saying that one should be generally true, right? So again, let's see, what is this saying? Let's look at one direction here. Maybe this direction this way. So if you're able to satisfy A or alpha, that means you found a truth assignment that make this guy true. Now, if you found a truth assignment that make this guy true, will that make this guy true as well? Yes, right. And the other case is symmetric. And then you can check the other direction. This is always true. The tricky part is the second one. The second one is not generally true. All right. And let's look at a very concrete example. This is like a trivial one. If I tell you, let's look at sat of x and not x. So a variable and its negation, right? Now, this guy alone is satisfiable. I can always set this to true and then I will satisfy it. And not x is also satisfiable because I can set x to false and I will satisfy it, right? The problem is in this case, even though x alone is satisfiable and not x is satisfiable, their conjunction is not satisfiable. And the problem is the way I satisfied x conflicts with the way I satisfied not x. So the solution I found to this part of the problem is incompatible with the solution I found to that part of the problem. That's why in general, number 2 does not hold. But if we have decomposability, what does that mean? That means these formula A and B do not share variables. So that can never happen. That is, if you go and find a way to satisfy this, a variable assignment, and then you find a way to satisfy that, you can do that so that the solution you found here does not conflict with the solution you found here, and you paste them together and you end up getting a solution for the conjunction A and B. See what's going on? There's no interaction between these two subformulas, and therefore I can solve them independently. Okay, you can see now, satisfiability on Boolean formulas is governed by 6 equations in this case. Under decomposability. And what does this allow me to do? Well, let's look. So let's apply this to this particular formula or this particular circuit. We start at the bottom and move up, right? So if you look at the bottom, everything that we have at the leaves is basically literal. So they're all satisfiable according to our equations, right? So far, so good. And now we move up, and then we're going to do these OR gates because we're ready to do them because we have the answers for the children. And what did we say? An OR is satisfiable if and only if one of its children is satisfiable. So in this case, I'll end up getting a yes for all of these guys. And then I go to the next layer because now I'm ready to compute the satisfiability of these. And what did we say? An AND will be satisfiable if and only if all of its children are satisfiable. So I do that and yes, and then finally yes. So this whole thing is satisfiable. Okay, pretty simple, pretty nice. And I have a question for you now. You probably is wondering, someone already wrote this question. The question is, are all decomposable circuits generally satisfiable? Because you're looking at this saying, how can I ever generate a no? Correct? Okay, anybody can answer that. So this question can be a qualified yes. How can I ever generate a no satisfiable in this case? How can I end up generating a no at the top? Okay. Someone already said true and false. Okay. You can have these guys at the bottom, right? So the leaves are not always literals. You could have constants true and false. And the way to answer this question is, you're right. If you do not have false as at the leaves, you cannot generate. This will be satisfiable. The only way that this would not be satisfiable is if you had some leaf nodes labeled false. Very good observations. Now you're going to say, how would that happen? We'll see this in just a little bit. Okay, very good. Nice. Let's move on and go to another operation. It's interesting because satisfiability is the prototypical problem for the class NP, and that's a very important class. And this is one property that pretty much unlocks that complexity class. If you know how to enforce decomposability, you pretty much own the class NP, which is pretty interesting. There's a question, how can not A and A both be set to yes? Right. Well, as we mentioned, when you are doing this, you're thinking of this as your only problem. That's it. I'm giving you like the formula not A, and I'm saying, is that satisfiable? And then when I'm doing it here, I'm giving you the formula A. That's it. And I'm saying, is that satisfiable? And I'm not telling you how they're combined. I'm just telling you they're independent problems. Tell me, is this satisfiable? Is that satisfiable? Okay. Now let's go ahead and move on. Here's an example that you guys were talking about. So if I go ahead and do this, so what I did in this case is I replaced this guy with false, so A with false, and similarly this by a constant, and I got this. Okay, so I'm just giving you a variation. Question: is this decomposable? Now, it was decomposable before, right? This is what we looked at. And all I did is I substituted some of the literals for constants. And the question, does this remain to be decomposable? Someone is saying no. Why? Remember, what is decomposability? Decomposability is that if you look at AND gates and you look at the subcircuits that are feeding into them, they do not overlap in terms of variables. By fixing the value of some literals to constants, all I did is just removed variables. If I had no overlap, I will continue to have no overlap. Okay, so the question, the answer is now corrected to be no overlap. Okay, so remember this because this is going to be an important observation. If you take a decomposable negation normal form circuit and replace some of the literals by constants, it remains to be a decomposable negation normal form circuit. Okay, so now you can see if you do this SAT, if you try to check SAT on this, you will end up getting, at the top. So this now is unsatisfiable, okay? So it is a decomposable negation normal form, but it was unsatisfiable, and because I had some false at the leaves. Okay, guys. Let me mention just one quick concept here before we go to the next query. The notion is that you can sometimes talk about a partial notion of decomposability, because now we say, is the circuit decomposable? Yes, no. Sometimes it makes sense to refine this a little bit further and say whether it's decomposable on a particular variable, meaning is it decomposable on B? Meaning if you look at any AND gate and you look at the subcircuits feeding into that AND gate, will B, the variable B, end up being shared? So this is a little bit more refined. And when you look at the circuit from that point of view, you'll see that it's almost decomposable. The only exception to the rule is this variable, OKZ. This circuit is not decomposable on OKZ. It gets shared by subcircuits. So if you look at this guy here and you look down here, you find OKZ. If you go down here, you find OKZ. But it is decomposable on everything else. Okay, bookmark this. We'll make use of this observation in a little bit. All right, so in this case, we will say that this is decomposable except on OKZ. Okay, let's go now to the next operation, which is clausal entailment. So remember, what we've handled so far is consistency, CO. We called that CO before. And you now see that with decomposability, consistency or satisfiability can be done in polytime. Now we're going to look at what we call clausal entailment, CE, that operation. And we will have to see what happens here. And that actually will tell us a little bit more about these circuits and what you can do with them. So what we're interested in is this kind of a question. We have a knowledge base, which is in the form of decomposable negation normal form, d-DNNF. And then I have a clause. So these are literals. Each one of these is either a variable or its negation, right? And I want to check that entailment. And the claim you can do that in linear time as well. Okay, so you can check whether a d-DNNF implies a clause. You can do that in linear time. And now we're going to see why is that the case. What we're going to do is we're going to start by employing what we call the refutation theorem, right? So what is the refutation theorem of people remember? I'm trying to, if we call this alpha here, this clause alpha and this circuit, we're trying to do this, right? We're trying to check, does delta imply alpha? And the refutation theorem allows me to reduce that to a consistency test or a satisfiability test. The refutation theorem is what we refer to as proof by contradiction. To do this, I need to check if this guy and the negation of that is inconsistent, right? So for us here, it would be this. That is, I check the satisfiability of this. If this is not satisfiable, then I've shown a contradiction, and then I will say, yes, the clause does follow from the knowledge base. So let's see how we can do this, because now you say, well, good, we reduced it to SAT. I know I can do SAT on these circuits easily, so pretty much I'm done. Well, not exactly, because now I need to do SAT on this guy, not on the original one, right? So here's my circuit, and let's take a concrete example here. And I want to check whether this circuit is consistent with the literal A. So what you can say is, okay, good, let's just conjoin them. Now I have a new circuit that represents the conjunction and run SAT on it. There's one problem here. What is that? So this is my original d-DNNF. This is a d-DNNF circuit here, right? And I'm trying to check whether the conjunction of that circuit with the literal, positive literal A is consistent. So we're saying, do this, and now go do satisfiability. Now we know that satisfiability is linear on d-DNNF circuit. Someone is saying this is no longer decomposable. So this is a d-DNNF, but when you do that, this guy is not d-DNNF. Okay, I lost decomposability because look, I have A here appearing, and if you look at down this branch, I have A appearing there as well. Okay, now it turns out that there is an easy fix for this. Okay, and the easy fix is from the following identity, and you need to remember this. This is pretty important identity. If I have any knowledge base or any formula, Boolean formula delta, and I'm interested in conjoining it with a bunch of literals, all right? So that this is always equal to, if you take this guy and condition it on L1 Ln, and then conjoin with L1 Ln. Remember what conditioning is, because what is a literal? A literal is either positive or negative. So you can think of a literal as declaring the value of a variable, right? So if I have the literal not x, I'm kind of telling you x is false. If I have the positive literal x, I'm telling you x is true. The fact that you're conjoining with these literals is like you're conjoining with information that fixes the value of these variables. So what I can do is I can say, okay, let me take my formula and let me condition on these literals. That means fix the value of each one of these variables according to what the corresponding literals say. and then I conjoin with that. So these are equivalent. What does that mean? That means since I'm conjoining here with the positive literal A, I can go and substitute the value for A in this guy here, okay? And that's what's going on here. A appears in two places. Now, since I'm conjoining with A, meaning A is true, what do I put here? I replace this with a constant true. And then I replace this with a constant false. If I do that, I'm basically conditioning this circuit on A being true, right? I just replace these guys with constant. What did we say about that? This remains to be decomposable. Now I can conjoin. Okay, so now what I have is basically a d-DNNF that represent the conjunction. And now I can do SAT on this. So let's see this with a full example. We recall that this circuit here represents this particular device. And let's say I want to check whether this behavior of the device is possible, right? This is that both gates are okay. So both inverters are functioning properly. And yet the input to this device is high or true and the output is false. Question, based on your knowledge of this guy, is this actually a possible behavior? Yes or no? And people are saying no, right? Because if I had high, it becomes low and then it becomes high. So these guys must be the same if the two guys are functioning properly. So if I check the consistency of this with that, I should get a no. And the way to do it in this particular case, if I want to reduce this to a satisfiability test on a d-DNNF, I will go ahead and do the conditioning, right, as we did before, right? So I'll end up for the variables A, C, okay, X, okay, all of them will be replaced by constants, all right? So actually the only free variable still is B. And here's what I have. And if you want to think of this as this new d-DNNF circuit, it's already decomposable now, and I can go ahead and propagate the values, and then I'm gonna get basically a no. Okay, so far we know how to do satisfiability, we know how to do the transformation conditioning, and we know how to do clausal entailment all in linear time. Okay, now remember this notion of decomposable except on some variables, where we said this is a circuit, it is decomposable on every variable but okay, Z. Well, it turns out these are still useful in the following sense, that you can still do clausal entailment on these guys in linear time as long as the clause that I'm checking mentions all variables on which we do not have decomposability. Right? This is what's stated here. And you can see why, right? Because if I have this guy and I'm trying to conjoin it with this, I'm going to replace those occurrences with constants. So even though this circuit was not decomposable on this guy, when I substitute a specific value for that variable, then it is decomposable. Just pretty interesting. So in a sense, you can talk not just about something being decomposable or not decomposable, but there is a shade, and those circuits that are not decomposable on certain variables can still be useful in this regard in answering some kind of queries. So I have a couple of questions. What does OKX mean? OKX means that that gate is behaving as intended. So if it's supposed to be an inverter, if it is okay, then it will be an inverter. Now, some of the people may be asking, what happens if it's not okay? The way we did it so far, we're completely silent. We say, we don't know what's going to happen when it's not okay. Now, we're going to get to the subject in more detail later when we talk about the application of diagnosis, because this is one way of doing things, but it is sometimes you will need to, there's the notion of fault modes of devices, and we will study this in more detail later. Actually, it's a fascinating application there. Let's do one more operation before we go to our break. All right. Now, you remember this guy. We called it existential quantification or projection. And the idea was that you have a knowledge base like this. In this case, it says A implies B, B implies C, C implies D. And what I want to do is existentially quantify some variables. In this case, let's say we want to existentially quantify the variables BC. We call that also forgetting the variables BC or projecting on their complement AD. And intuitively, we said that this is like removing those variables from the knowledge base while keeping all of the information that the knowledge base had about the other variables. So in this particular case, this knowledge base says that A implies D. And that's actually the only thing it says about these two variables. So the idea, if I existentially quantify B and then C, then I should get a knowledge base that's equivalent to that. And we said two things about this operation. One of them is the formal definition that if I want to existentially quantify a variable from a knowledge base, I take that knowledge base, condition it on X, the positive literal. That means I fix the value of variable X to true here. And then I go and fix the value of X to false. So I get two things and I disjoin them. This is a simple thing for a single variable. If you do this for multiple variables, this is not efficient. You're going to get an exponential expression there. And we said one thing about doing existential quantification in a different way, if you remember using resolution. You said if you take for a CNF, if you have a CNF and you want to existentially quantify this variable, close under resolution on X, that is, do all possible resolutions you can do on the variable X. And after you do that, just go ahead and remove all clauses that mention X. This was one thing. And now we're going to see what happens when so this is still quite a bit of work, right? You have to close under resolution, and this is for one variable. And if you want to existentially quantify more than one variable, you have to do resolutions on all of them. And we've seen what happens with resolution. Things may blow up as you may have so many clauses, inferred clauses. Well, you'll see now if you have decomposability, you can existentially quantify any number of variables in linear time. And the algorithm is surprisingly simple. I will show it to you first so that you can see it through an example. And then we will see again why that holds. So here's the example we'll look at. It's again what we've been looking at. Remember, this is a circuit that describes the behavior of this particular device. And let's say I want to go and project this knowledge base on these three variables, okay? Intuitively, what do you think is going to happen here? This device describes effectively, or this knowledge base describes the behavior of the X inverter and the Y inverter, correct? And if I were to project on AXB, that means I'm existentially quantifying these two variables. What do you think is going to happen as far as what I'm going to get as an output from a device description point of view? What would the result end up describing? I'm forgetting the information I have on OK, Y, and on C. All right. Well, you will get basically a description only of this inverter, and you will forget what you know about the Y inverter. But let's see first, how do we do that? How do we existentially quantify these two variables, which appear as follows in this circuit? It turns out to be very simple. If you want to existentially quantify a variable, all you do in a d-DNNF, all you do is replace every occurrence of that variable, whether positive or negative, with the constant true. So in this case, this will end up replaced by true, this will end up being replaced by true, and this will end up being replaced by true. And if you do that, you're going to get this circuit. Now, we already know this is still decomposable because all I did is I replaced literals by constants. And that is the result. If we're going to call the original circuit delta, then what we just did is we existentially quantified OK, Y, and C from that by doing this. And if you check what this actually represents, it will end up being this. It will end up being the description of the X inverter in this particular case. Now, why is this the case? Why did we get this procedure? And you can do the justification just like we did with SAT. You will have to consider 6 cases. And these 6 cases are, 2 of them are for the constant true and false, and 2 of them for the literals, positive literal, negative, actually a little bit more, yeah, two positive literal, negative literal, and then conjunction and disjunction. And you will find that in all of them, they end up being easy except for one case, which we're going to look at in detail next. But let me show you the cases. So there is constants, literals, and disjunctions. Those turn out to be easy, and what I'm going to show you here will work in general. And then there's the one case about conjunctions. So if you go and say, what if I'm existentially quantifying a variable X from false? You can do the definition of existential quantification, which is there exists X delta equals delta given X or delta given not X. We're going to use this because it's easy to use this in these boundary cases. So if you check this, you're going to get false. So don't touch this. If you're existentially quantifying the variable from true, you're going to get true again. If you go ahead and existentially quantify X from some other literal Y, positive Y, and apply this definition, you're going to get Y back. If you do this for not Y, you're going to get not Y back. So again, using this definition. Now, if you're existentially quantifying the variable X from the variable X, you will find out using this definition that you're going to get true. If you're existentially quantifying the variable X from not X, you're going to find true. All of these cases follow by simple application of this rule. These are the base cases. So the base cases said, for constants, don't touch them. They stay the same. For literals that are not about X, keep them as is. Only the literals that correspond to X, flip those to true. The other case that remains is for the disjunction. You know, what if I want to existentially quantify the, X from a disjunction? And again, simple application of this will show you that this is the same as existentially quantify from alpha and existentially quantify from beta, and then put the results together. So far, if look at this, these equations, and suppose your circuit doesn't have AND gates. Suppose your circuit does not have AND gates. These equations already tell you what we did is the correct thing, right? Because it says, the only thing you need to do is these guys. But of course, our circuits have AND gates. And in general, there exists X out of alpha and beta. In general, this is not equal to there exists X out of alpha and there exists X out of beta. This is not in general true, but as you're guessing, we don't have arbitrary conjunctions in this case. We have the fact that alpha and beta do not share variables. And in that particular case, this ends up being true. And here's the derivation. It's straightforward application of this definition that I just mentioned. So you take this guy, and I want to existentially quantify X from this. If you apply the definition, it says condition this on X or condition this on not X. That is, fix the value of X in these two guys. So that I can do here, fix it in this, fix it in that, dot, dot, dot. So far, good. The difference here is that in this case, I know because of decomposability, X cannot be part of both delta and gamma, cannot. So without less of generality, as they say, let's assume that it only appears in gamma, but not in delta. So what happens in this case? Look at this guy, because X does not appear in delta. So when I condition delta on X, I get X back. And similarly here, because X does not appear in delta, okay. So now look what happened. I had this guy and suddenly becomes this. I can pull the delta out and now I have this. And this is nothing but existentially quantifying X from gamma. So I got this guy. Now, since X does not appear in gamma, that's the same as saying also there exists X delta. Okay, because this will give me back delta. X does not appear there. So look how nice. We're back to the same thing where we basically just did a pass. In this case, we didn't even have to do a pass through the circuit. All we had to do is change some of its literals. And that's actually pretty remarkable because existential quantification, especially of any number of variables, is pretty difficult on almost everything we're going to look at. But it is actually easy when we have the decomposable negation normal form. So we're going to take our break now while realizing that we have already shown how you can do satisfiability, how you can do conditioning, how you can do clausal entailment, and how you can do existential quantification, all pretty easily on these circuit types. And when we come back from our break, we will look at least one more interesting operation, which does not appear in the list that we talked about, but has a lot of applications, particularly to diagnosis and explainability later. So let's take our 10-minute break and resume our discussion after that. Thank you.